This is Teacher Naihma, and welcome to another video. Today we'll be talking about intermolecular forces and their boiling points. Now, without further ado, I think let's start. Now, I hope you still remember the periodic trends that we have talked about earlier or in our previous lessons. So, if you don't remember, here are some refreshers for you. So, every column is a group. Oops, the spelling is wrong. And every row is a period. Now, if you're going to talk about what kind of elements there are or what kind of element that is, you're going to look at the legend right here. It will be all color coded. So the alkali metals will be in red. It's right here. The alkaline earth metals will be in orange. The transitional metals will be in yellow. The basic metals will be in green. And then you have etc. etc. You have semi-metals, non-metals, halogens, noble gases, lanthanides, and actinides. Now, a lot of the elements that are found here on Earth, most of them are metals, and only a few of them are non-metals. So the very, very short ones are, if you look at this in the periodic table, there is sort of this ladder right here, which divides the non-metals from the metals. This is the ladder. So the ones on the right are all non-metals, and the ones on the left are all metals. So again, there are only a few that are non-metals. So let's go to the IMFs, or the intermolecular forces. We're going to talk about four main types, or we have already talked about that in our previous lecture. So you have learned that there are four main types of IMFs. You have the London dispersion forces, the dipole-to-dipole forces, the ion-to-dipole forces, and the hydrogen bonds. And if you look at the arrangement right here, as you go from 1 to 4, the IMF is more strong. So that means that the London dispersion forces would be the weakest of them all, and the hydrogen bonds would be considered to be the strongest, not considering the ion-to-ion ones. Now, if you remember during our lecture, we talked about London dispersion forces. London dispersion forces are also known as your van der Waals forces, and they are found in all of your compounds. So this is sort of like the entry level force. So all of your compounds, all of your molecules will have this type of force. Then you have the dipole-to-dipole forces, which are found in molecules that are polar. So they are polar molecules. Your ion-to-dipole forces would have a metal and a polar molecule. And then your hydrogen bonds are basically with hydrogen, but hydrogens that combine with F, which is fluorine, oxygen, and also nitrogen. So F, O, and N. So you just have to remember that. There are only three. So these are the things that you have to remember. Not all the time, but you just have to familiarize them. So in this activity, we're going to identify the intermolecular force that exists between the following molecules or the basic units of the following species. Okay, let's start with xenon. Now, what is xenon? Because it is a noble gas. That means that if it's a noble gas, it doesn't really have to exist with another element. So it can be existing on its own. So what if a xenon exists? Would that be London dispersion or polar or dipole to dipole? What is it? So because xenon is only one element and it doesn't bond with other ones, or if it ever bonds with another xenon, it will have the same electronegativity. So since it will have the same electronegativity, there is no polarity there. So no polarity at all. So which of the four IMFs would have no polarity considered? So that would be your London dispersion forces. So you can just write London dispersion force. Okay, so that's what IMF exists in just one single xenon atom. Now, what about CH3OH? Now, what is this? Is this polar? Well, definitely it's not, because it doesn't have metal. Definitely it's not going to be ion to dipole. But the question is it polar or non-polar? Now, let's look at the geometry of CH3OH. So that is the most accurate way of looking if it's polar or non-polar. Now, this would be the molecular geometry of CH3OH, because it's going to transfer my face right on the left. Carbon would be the central atom, and carbon would have a greater electronegativity than your hydrogen. So a lot of the electrons would go towards carbon for all of the hydrogens. But there is an O and an H right here. Now, if you look at the periodic table, O would have, or oxygen would have, a greater electronegativity than carbon. So those elements that bond to oxygen, their electrons would go towards oxygen, and oxygen would be partially negative. So what does that mean? That means that all of these arrows, they do not point towards one direction. They point towards different directions, actually. Some of them would point towards carbon, and then some of them would point towards oxygen. So that would mean it has a polarity. So you would say that CH3OH would have an IMF of dipole to dipole interaction, or dipole to dipole force. Okay, let's look at the second set of examples. You have iron trichloride. I think this is very obvious, right? If you look at iron, iron is a metal and chlorine is a non-metal. Iron is, what type of metal is this? Iron would be in the transitional metals. So this is a metal and this is a non-metal. Sorry, non-metal. So which of the four would have a metal in them? That would be ion to dipole interaction. Now what about NH3? Now if you look at NH3, it has hydrogen. So if you remember what we talked about before, hydrogen bonds are very strong, especially if they bond between, if it's a bond between hydrogen and either of the three elements, F, O, and N. Now, if you look at this example, it has N in it. So this would be a hydrogen bond. So that's the main IMF that exists in NH3. Now, what about CHCl3? So CHCl3. Now, is this, if you look at this, is there a polarity or none? Let's see. So CHCl3, if you look at the molecular geometry, I think that's the absolute way of determining if it has polarity or not. Now, carbon would be the central atom. So this would be carbon right here. And then this would be chlorine and chlorine and chlorine. And the small little ball would be hydrogen. Now, carbon would have a stronger electronegativity than hydrogen. So that is why the electrons that are in hydrogen would travel, or not travel, but it would spend most of its time to carbon. But then chlorine would have a larger or a higher electronegativity than carbon. So the electrons that are found in carbon would spend more of their time towards the three chlorines. So the direction, is there only one direction? No, there are many directions. There are two directions actually. So since there are two directions, there would be a polarity. So you would consider this as dipole to dipole interaction. How about carbon dioxide? Now, if you look at it, you would say, oh, I think it's London dispersion because it's just carbon and oxygen, right? Let's look at the geometry. Now, carbon and oxygen, when they bond, mm, they would have, it would probably look like this. You have 6 valence electrons for oxygen and then 4 for carbon. So you would donate 1 pair to oxygen so that it would be happy, but then carbon will lack still. It would lack 4. So you would donate 2 more. Okay. So if you look at that, you would have a lone pair here, and then oxygen will also have a lone pair here. So oxygen would be happy, so 2, 4, 6, 8, and then carbon will also be happy. So the molecular geometry would probably look like this, but then look at the electronegativity of both of these elements. Carbon would have a lesser electronegativity than oxygen. So a lot of the electrons in carbon would spend most of their time in oxygen. So oxygen will be partially negative, carbon will be partially positive. So that means there is a polarity. So carbon monoxide is still, or it also has a dipole to dipole interaction as its main IMF. Okay, now what about for the boiling points? Which would have a higher boiling points? And I'm going to show you some examples after this. So here are some pointers to determine which would have a higher boiling point. Number 1, look for molecules with hydrogen bonds because hydrogen bonds have stronger, or it really has, or hydrogen bonds are the strongest among the IMFs, excluding, of course, the ion to ion um, ion to ion IMF. And then look for molecules with dipoles. If there are no hydrogen bonds, let's look at the dipoles. The dipoles usually win, okay? But if both of them are dipoles, you have to look at the atomic size, okay? Larger, or the third one would be larger molecules will have stronger London dispersion forces. So if you are confronted with 2 examples that both have the same IMFs, like the London dispersion forces, you're going to look at the atomic size of the molecule. Okay, so let's go here. Now, which substance in each of the pairs would you expect to have higher boiling points? Now, oxygen gas versus chlorine. Okay, 2 atoms of chlorine. Now, if you look at here, because it's just oxygen to oxygen and chlorine to chlorine, they don't really have um, a lot of difference in electronegativity. So if oxygen will bond with oxygen, they have the same electronegativity. And chlorine, the change in electronegativity would be 0, and this one as well. So both of them would have London dispersion forces, but which would have a higher boiling point? Now, if you remember in periodic trends, when you go from left to right, the atomic size would increase. If you go from top to bottom, it would be the same. The atomic size will also increase. Now, if you look at your periodic table right here, I have a periodic table printed out. I printed out one. You would see that chlorine would be a little bit further on the right than oxygen. So that would mean that chlorine will have a higher, or not a higher, but a larger atomic size. Therefore, which will have a higher boiling point, it would be chlorine. So chlorine will have a higher boiling point than oxygen. Now, next example, you have HF, hydrogen fluoride, and HI, hydrogen iodide. Now, I think it's very obvious. Both of them have hydrogen bonds. Okay, so their main IMF is hydrogen bonds, so H bonds, so both of them. But then, which would be the winner? Which would have a higher boiling point? So you're going to look at fluorine here and iodine here. Between the two of them, which would have a bigger atomic size? Now, if you look at the periodic table, fluorine is in period 2, and iodine would be in period 5. So if you look at the periodic table, so fluorine would be up here, and then iodine would be somewhere here. So it's below fluorine. So that would mean that iodine would be heftier than fluorine. Therefore, hydrogen iodide will have a higher boiling point. Okay, now how about this one? CH4 versus Cl2. Okay, now we have established that Cl2 has London dispersion forces as its main IMF. So both of them, for Cl2, this would have London dispersion as its main IMF. How about CH4? Now, if you look at CH4's molecular geometry, it would look like this. And then, because carbon has a higher electronegativity than hydrogen, all of these electrons will travel or would spend a lot of their time towards carbon. So that would mean the direction is singular. So there's only one direction. That means there is no polarity here. So this would also have London dispersion forces as its main IMF. Okay, so let's determine. So between the two of them, CH4 and Cl2, which would have a higher boiling point if that's the case? Now, if you look at chlorine, it is in period 3, and that would mean that it would have a higher atomic size versus carbon, both carbon and hydrogen. So that would mean that chlorine will have a higher boiling point. So that will teach you to remember that although they have the same IMFs acting upon these molecules, you also have to look at their atomic size. Okay, how about this one? This is silicon tetrahydride versus tin tetrahydride. Okay, let's look at what type of elements they are. Silicon is a non-metal. Tin, on the other hand, it's a metalloid. So silicon tetrahydride will be, will it be, its weakest IMF it would at least have a London dispersion, at least. So we don't know if it is polar or not, but that doesn't matter. Why doesn't it matter? Because we already know that tin is a metalloid, so it will have an ion to dipole force as its main IMF. And you know that ion to dipole force is stronger than the dipole to dipole and the London dispersion forces. So that would mean tin tetrahydride would be or would have a higher boiling point than silicon tetrahydride. Okay, so I hope you learned a little bit or a lot in this video, and good luck on answering your worksheets. Now, do not forget to believe in yourself. So see you in the next video, and comment if you have questions. I will always respond to them. Goodbye.